let's recall. I could copy paste, or I could just, I think we can get almost all of it. If phi, so we started with phi if phi is on gamma naught n, meaning invariant under gamma naught n and a Moss form. Then phi has this expansion with an's, some Whittaker function of y, e of nx. Okay. Then we saw that phi twisted by chi, which is an chi of n, Whittaker function, is also on something. It's on something like maybe not gamma naught but gamma 1, and maybe not n but nd squared, where d, so this is for all d coprime to n, and chi primitive mod d. For example, I mean, I just need some invariance. I needed the diagonals to be the same, yada yada. And
zero, but intersect.
yeah, this is enough for our purposes. Now, chi, the expansion, the Fourier inversion, the result of Fourier inversion is a formula like this. If you take chi m bar, e to the 2 pi I, let me write it as e to the 2 pi I m n over d. Right? And when we stuck that in for here, we got that phi chi of z is chi of -1, tau of chi over d, this finite sum, m mod d. Of course, the only m's that occur are the ones that are coprime to d, chi of m bar. And then this, the only thing that did is it affected the x, and we got just phi of, you could put d, I'm going to try to keep things determinate 1 now, m over d 0, 1 instead of dm 0 d. Last time I was trying to keep them integers, but it doesn't matter, acting on z.
Action is the same.
The action is the same. Okay, so this is one formula. Then, because this phi thing is on gamma 1 n squared nd squared, we considered phi chi of w n d squared z.
These normalizing tricks make things perfect.
Yep. And remember that this we define this function psi of z to be phi of wn z.
Right.
Okay, so when we did this out, we got the same beginning part, chi -1 of d, tau of chi, really, I think of tau of chi over d, a sum over m coprime to d, chi of m bar. And then instead of phi, we put psi of wn inverse, then we put this thing, which was here, 1 m over d 0, 1.
We use this with size of chi should be.
Right. Then instead of z, I'm going to put wn squared, wn d squared, z. And into here, I'm going to insert 2 more things, a 1 instead of m l 0 d, and a 1 negative l 0 d. And this whole thing, when we multiplied it out, this is the one place where I'm going to cheat and recall the outcome of this calculation. It might actually be faster to redo it than to find it. Okay, so I'm not going to cheat. I'm going to recall what the outcome of this calculation was. It's something very simple. Just need to be able to see it. Okay. So 0, what's wn inverse? -1 over n, not n, but nn 0, 1, 0. Right? That's this wn inverse. Then times 1 m over d, d needs 2 d's, 0, 1. Then times 1 negative 0 negative 1 n d squared 0. And finally times 1 negative L over D and 0, 1. Okay. Simplify and matrix form. Beautiful. And I can divide this by D. And if I divide this by D, I get something that's similar to, just reminding you, negative D L mn and this thing, so I'll call that thing S.
Determines what L is.
Yes. So I don't know if that looks funny. This thing is similar to this, where negative ds, I guess I can do, I really get a negative d? I want a positive d here. Well, I can do that with this. I can negate everything and I can change the definition of S. Because it's at PSL or PGL acts. Okay, so ds, I guess, plus LMN equals 1. Okay, and L has to be determined. L is, this is true for any L, so I can choose such an L. Okay, I'm just reminding you what we did last time. Now, what we said last time, we know that psi is on gamma naught n itself, and this matrix is then in gamma naught n, which means I can cross it out. Okay, but let me just record this fact that phi psi, this, that was our assumption. I mean, that's a consequence of the fact that phi is assumed to be on gamma naught n. And that's how we showed that this phi psi thing gives us this functional equation. Okay, so I'm just going to record this formula: chi of -1, tau of chi over d, a sum. I'm going to change from m's to l's. So L is congruent to -mn bar mod d. So I get out a factor of chi of -1, chi of m bar is chi of L, and then there's a factor of chi of n. Yes. And then instead of summing over m mod d, I can sum over L mod d coprime. And then what I get is phi. Now I'm not going to erase this matrix. I'm going to keep this matrix here. D negative L minus mn s times 1 L over d 0 1 s z. So, okay, this is just what we did last time. From this, we got the functional equation. Oh, we also recognize this. Okay, so I need one more step. The chi of -1s cancel. The chi of n pulls out. The tau of chi over d stays. And then I have a sum of L over d coprime. And we recognized, sorry, it's this, where is it? This.
Yeah.
This formula is true also for psi. And so, so we recognize this whole thing as psi, except here I have the chi of n comes out, and I'm supposed to have a tau of chi L bar here when there's a psi here. Let me just write it, and then I'll explain. This whole thing comes out to this times psi chi of z. That was the key. Chi bar. Thank you very much. Exactly. Chi bar. Okay. When you use this invariance, then this whole sum becomes very close to psi of chi bar, and the amount that it's off by is that there should be a tau of chi bar, which we can do with this. Okay. From this, we got the functional equation. This implies that if I take the completed L function of phi twisted by chi at s, and I multiply it by this factor nd squared to the s over 2, that's this nd squared. When I integrate this thing by itself is the integral of phi iy. I get rid of this y to the 1/2 and y to the s dy over y. That comes out to the completed L function. I multiply by this factor. I make a change of variables. Y goes to negative y over. I make a change of variables. Y goes to 1 over y nd squared, which has the effect of applying this. Now I put it into this formula. And that gives me something similar with an n d squared, not to the s over 2, but to the 1 minus s over 2. And then the completed L function. Oh, and then a couple more things. The root number chi of n, tau of chi squared over d, which has absolute value 1. And then the completed L function of psi twisted by chi bar at 1 minus s. So this is all we did last time. Okay, I'm going to need all these formulas. So the Weil converse theorem is how much of this is reversible? How much of this goes the other way, is reversible?
So you're gonna give up the
Yep.
automorphicity.
Exactly. So again, assume we have this sequence A and Bn, we have these L functions, and we have and there exists an n, an eigenvalue lambda, and an n, so that for all d coprime to n, and for all Dirichlet characters mod d, only those that are primitive, will have this nice functional equation with the tau. Okay, this is going to be the crucial thing that makes this theorem hard.
We're doing things with Gauss sums along the way, right?
Yes, yes.
So
So
gets
that's,
messed up, like if you-
yep, we'll get the wrong functional equation. We'll get the wrong terms here if it's not primitive. Assume that there's a sequence so that for all chi primitive, this L function, L1 chi of s. Well, let's just call it big L, lambda 1 pi s, which is the completed L function, 2 pi to the minus s. These gamma factors, s plus IR over 2, s minus IR over 2. R, of course, is a quarter plus r squared is lambda.
you know, they're always in there.
Laplacian, times the L function a n chi of n over n to the s. Assume we have one of these and we have the same thing, assume we have sequences a n b n, a complex number lambda, really a positive real number, never mind, natural number n, so that for all d coprime to n and all primitive characters mod d, if this thing has analytic continuation, bounded in vertical strips, so we can pull contours, bounded in vertical strips.
Usually you just ask. Literally not, right? So you take 2 sigmas and then make sure that it's not.
And then the gamma factors, I asked out of the L function, the gamma factors tell me I have decay. So I can take the ends off and pull the vertical strips. And functional equation, which is this functional equation. Okay.
Well, chi including the trivial one.
For all chi, including when d equals 1, d is 1 is coprime to n. Pi, the trivial one is primitive mod 1.
The trivial one was what we showed would not suffice, right?
That's right. That's right. Precisely because this element Wn is not in the group. It doesn't generate the group. We just get one functional equation. There's not enough to guarantee generation. Right. So then the function phi, defined as an, this Whittaker function with that eigenvalue lambda, e to the 2 pi n x, is automorphic with respect to gamma and pi. Okay, so that's the theorem. So how much of what we just said to derive the functional equation is invertible? Okay, first of all, we can take this, which is this, we can recover from the L function the Mossel. We don't know that it's a Mossel, we don't know that it's invariant, but we can recover the function. So by inverse Mellin transforms, as before, we learn this formula. This formula here. Let me call this formula 1. Let me just write it and then I'll answer your question. We get 1, which is phi chi. They do get in the way. The chi's are there.
Yeah.
The chi's are there. Phi chi of what? This, we only know it on the vertical line, but in a second, we're going to know it in general. I over n d squared y is equal to, right here, chi of n tau squared over d psi of chi bar of I1.
I guess my question is the inverse Mellon transform goes through the same as last time.
The same as last time. Yep. Yep.
Nothing fancy.
Nothing fancy here. Just apply the inverse Mellon transform to the functional equation, and you get this. You get it on the line. These functions satisfy the differential operators that allow you to conclude. That allows us to conclude that it's actually true for all z. And in fact, because Wn is an involution, it'll be more convenient for me to put it over here or over here. Let me leave it where it is. So, so this allows me to conclude that Wn d squared z is just the same formula, but now it's not on the one line. Tau of chi squared over d. So we get the functional equation in the L functions. We take inverse Mellon transforms. The inverse Mellon transforms, on one hand, it's on one hand we get, well, okay, really, when we take the inverse Mellon transforms of the L functions, on one hand we get this, on the other hand we get this, but it's an involution. I don't need the equation one. We get this, this L function, if you take the inverse Mellon transform, and of course it has these factors n over d on one hand, you get this. On the other hand, by the assumption of the functional equation, you get this, which amounts to this. Take a second to think about it if you want, but basically we work back to here, and then we replace. First of all, we show that there's a y missing. Y. We show that this holds not just on the vertical line, but everywhere. And then we show that, and then just apply the fact that WND is an involution.
Can you say a couple words of how we went from the line to everywhere?
Yeah, this is what we were discussing last time. Yeah, the analyticity. Yeah. Okay, so we have this chi, we have this phi chi. We have one formula for phi chi. We have another formula for phi chi. Okay, so this we get from the functional equation. This is from the functional equation. Now, what do we know about psi chi bar? Psi chi bar, let me leave this chi of n tau of chi squared over d. Remember what psi of chi bar is. Again, when we wrote out this formula, this did not use the fact that phi is automorphic with respect to anything. It's just, you take the definition of the Whittaker function, you stick in this formula for chi, and you get this identity. So this identity does not use automorphy. It's just putting in the inverse of chi and using the primitivity of chi. Okay, so this formula I will grab. It's true for phi, it's true for chi, it's true for any series. So this I'm going to replace with this in the appropriate context. So I have chi of -1, tau of chi bar. By the way, this is tau of chi over chi bar. Very convenient. Over d, a sum over m mod d of chi bar, which is now chi. And then this is psi of 1 m over d 0, 1 z. Now I don't need this form. I just put it here so we remember, so I could stare at it while I wrote out what this thing is.
The d's are right in the formulas written here.
The d's?
Yeah, so we have tau. The reason why we got a d was from this conversion.
The d is part of the functional equation.
Oh, I guess like for the tau, like for the Gauss sum.
Yes.
Like we had, yeah, the factor d just came from the conversion.
That's right. Okay, so that's one formula. That's one identity. This one is from the functional equation. This one is from expanding psi chi squared. This is expand psi chi bar. But we also have another formula for this, which we worked out in general, and that was right here. That was right here. In fact, that is, it's right here. I'm going to grab this formula. I'm going to grab this formula, which also did not use anything about automorphic, right? Let's stare at this for a second. All I did is I said, if you have a series with this chi and you stick in a WND squared, you multiply all this out. The psi I'm defining to be the other function. Psi is the function with the WN inverse in there, and then you get this series.
You get that formula, then you won't be able to cross things out.
I won't be able to cross things out. Exactly. It's the crossing out that I want to prove.
Yeah.
So I just want to have this here for a second while I jot down this formula. So this is chi of -1, tau of chi over d, a sum over, this turned into a sum over L, if I recall, right? I want to sum over L. We made this change of variables. The chi of M turned into a chi of -1, chi of L, chi of N, right? This thing turns into those things so that I can sum over L mod D instead of summing over M mod D. And then this was psi of this matrix D minus L minus M N S times this factor, this remaining factor 1 L over D 0 1 Z. Okay, and I can erase all of this. So all of that we got without assuming automorphic. So that much of the proof of the functional equation for the L function is reversible.
Inverse Mellon transform.
Just inverse Mellon transform and use the formula for chi in terms of exponentials and the replacement of multiplicative characters with additive characters. That's all. And now I'm almost done erasing. Okay. Now let's stare at these two formulas side by side. So this was expanding phi chi of W n d squared. Right? Now let's stare at these two formulas. I have a chi of n and a chi of n. I have an over d and over d, tau of chi bar and tau of chi bar already cancel. I have a chi of -1, chi of -1, tau of chi, tau of chi. So what I have, here's the key starting place of the proof. I'm going to change the dummy variable here to also be L. So I have a sum over L mod D, chi of L, psi of 1 L over D 0 1 Z. That's this. Is equal to this. Everything else cancels out. Everything else matches. Is equal to a sum over L mod D, chi of L, psi of this thing, which is D minus L minus M N S, 1 L over D 0 1 Z. Well, at the moment, all I'm doing is just saying I have two different expressions for the same thing. I make them equal. There's some constants that cancel on both sides. Of course, what I want is that the reason these two identities are true is because psi is actually invariant under this matrix. But I don't know that yet. All I know so far is this holds for all primitive D. M is determined by, S and M are determined by ds. So M is a function of L and S is a function of L, determined by such that ds plus LMN is equal to 1. Okay. This is a coprime sum, not that it matters.
How, one of the expressions, so how did we get the two expressions just in a couple words again?
So it was a bunch of things. We got this expression from the functional equation.
Right.
The psi chi bar has an expansion. That expansion gives us the top equation.
That's just a definition.
It's the definition together with inverting the chi, expressing the chi bar in terms of additive characters.
And then the second expression.
And then the second expression was to go back to this formula. It's sort of what the derivation of this point. What we did is we opened this formula up when we got this. We used this invariance to get this, and we closed that back up to there.
Okay.
So all of that is reversible except for the invariance of psi. That's the key thing we're trying to prove is the invariance of psi.
Except for B and C getting two expressions, and then.
Okay.
Whereas before we went from one to the other.
Yep. So let's look at this. These functions, this function and this function, when projected onto some L, I mean, let's think about this in the framework of L2 of Z mod D cross. Right? This is a finite set, a finite group. We talked about how the characters, so all chi mod D form an orthonormal basis, for this vector space. And they're a nice thing to be able to project any function onto. So here what we're doing is we're projecting psi onto chi on both sides, and we're getting the same Fourier coefficient. If we could do that for all chi mod D, we would conclude that actually these two functions are the same as functions mod D, and that's true for any D. And so we must have this invariance. But we don't know this equation for all chi. We only know it for primitive chi. Now, if D is prime, the difference between primitive and not is just one function. It's just one character, the trivial character. Okay, so let's build up our ability to prove this invariance for all things by first starting with D prime. So assume that D is an odd prime. Okay, then what is the span? So the span of the chi mod D that are primitive, span of primitive chi mod D, I claim is L2, the thing that's orthogonal to the constant function, to the trivial character, right? This is the trivial character perp.
You got rid of one dimension.
Right. Okay. So the fact that I have this identity for all primitive chi means I have it for the span of the trivial primitive chi. So that implies, this implies for all functions, C, any function you want, from Z mod DZ cross to the complex numbers, that's in the span orthogonal to the trivial character that I don't know about. What does it mean to be orthogonal trivial character with sum of the C L mod D coprime equal to 0? That's what it means to be orthogonal to the trivial character, right? The things that sum to 0, like all the Dirichlet characters. All the Dirichlet characters, all the primitive characters will sum to 0. The trivial character is the only one that doesn't sum to 0.
Or you can use multiplying by 1 twice.
Yep. So this identity is inherited from knowing this for primitive characters. We know it for all linear combinations of trivial characters, but the primitive characters, but the linear combinations.
Wait, so the C's here are like taking up
Just any function. What I'm claiming is that I can replace the identity with chi by taking linear combinations of chi's and summing across chi's. I can replace the chi's by any function as long as it has mean 0. Because that's what the span of the chi's, the primitive chi's span L2.
Are an instance of these chi's are an instance of that.
They're a basis. The primitive chi's are a basis for this vector space. I have this identity in that basis, so I have the identity in any linear combination of that basis. Okay. So what can I do? Let's fix some R fix some R in Z mod DZ cross. And set C of L to be either 1 if L is equal to R, -1 if L is equal to minus R, and 0 otherwise. That's as close as I can get to picking off one element. I want this true for every single value individually, but I only have it on average. The span of the primitive characters is something that has mean 0. So the closest I can get to isolating a single element is to make it 1 on that element, -1 somewhere else so that it has a balance, so that it has mean 0, and 0 everywhere else.
I guess like minus R even with mod.
Yeah, mod D. Mod D. Yeah, this is all mod D.
Zero else. So it's, and since you chose this prime to be odd, this isn't odd.
That's right. Exactly. Exactly. Okay. Then what do we get from this formula? So I only have two values here. When L is equal to R, I get psi of 1 R over D 0, 1 Z. When L is equal to minus R, I get it with a minus sign, minus psi of 1 minus R over D 0, 1 Z. That's the left-hand side. What's on the right-hand side? On the right-hand side, again, I get two terms. One when L is equal to R with a plus sign. One when L is equal to minus R with a minus sign. So I get psi of D minus R minus MNS. M and S are still functions of R. So there's a different M and S depending on whether I have L equal R or L equal minus R. In fact, I'll need that fact in just a second. Here I get a 1 R over D 0, 1 Z minus, so that's the when C is equal to, when L is equal to minus R, then C is equal to minus 1. Psi of D, now instead of minus R, I have a plus R. Instead of a minus L, I have a plus R. I'll work out what these things have to be in just a second. And then I have a 1 minus R over D 0, 1 Z. So let's work out what this bottom row is. Remember, what I need here, the condition is that DS plus MNR is equal to 1.
Where you just replace the element.
So when I replace R by negative R, the S can stay the same, but the M turns into a negative M. DS plus negative M times N times negative R is also 1. So when R gets replaced by negative R, this minus Mn turns into a plus Mn. The S stays S. Okay? You buy that formula.
And again, all you used for this was saying that, right, there's expressions in this basis, right, the basis of orthogonal stuff. And so
I only have the identity for primitive characters. The primitive characters span mean 0 functions. I can only, so their linear combinations will get me any mean 0 function.
right, and so what you're saying is if you took one specific pi in this like
No, to get this function C, I need a linear combination.
right. But what I'm saying is that the expression we had before was like we're not using all the strength that we have.
Yes, we have this not just for this chi, but we have it for all.
Instead of using like all of them together.
Yeah. So the same identity with chi replaced by any other chi, any other primitive chi, satisfies the same formula.
This is like really where we're using like, oh, we have all of these pies.
We have all the chi's.
This is what makes this twisting in this Converse theorem possible.
Yes. Okay, let me move this to this side, and I'll move this term to that side.
Just begging for your analysis.
So let me clean this up a little bit. I have psi of D minus R minus MN S times 1 R over D 0, 1 Z, that was this term, minus psi of 1 R over D 0, 1 Z. Of course, I want this to be 0. Because this thing should be, psi should be invariant under determinant one matrices with a C congruent to 0 mod n. I'm leaving this alone. I move that to the other side with a minus sign. That's equal to, when I move that to the other side, psi of d r m n s with 1 negative r over d 0 1 z minus, that term's taken care of, minus this term, psi of minus r over d 0 1 z. Both of these things I want to be 0, but now at least I have them on either side. So whether r is positive or negative, I have this identity. This holds for all z. I'll replace z by 1 r over d 0 1 z. Just going to make a change of variables.
No, we have to work out what.
We have to work out with that, what both sides are going to do. On one side, I get psi of the same d minus r minus mns. Well, this thing, now I get an extra term. So now I get a 1 2 r over d. I'm not taking the inverse. Minus psi of, again, 1 2 r over d 0 1 z.
And the other one, the ones on the bottom.
The one on the bottom have converted into something clean. dr mns. The minus r over d is canceled by the r over d z minus, and this is now just psi of z.
The same fractional linear transformations are evolutions of the other half.
Yep. Okay, so far so good. I want to express this. I forgot something. That's annoying. No, I want, let's see, how easily can I change things? I think I can do it from here. I want to use both D and S for this purpose. I want to use both D and S for this purpose. So let me grab this formula. This formula holds as long as, or the formula above, I guess I could do it right here. What I want to say is this formula holds, okay, I can do it like this. This identity holds. This holds as long as D and N are co-prime. D is a prime. Odd prime, sure. Odd prime. I can say D and 2N are co-prime. D is a prime. And R is in Z mod D cross. Okay, and R is an invertible element. R is not 0 mod D. I want to say the same thing with D replaced by S. Similarly, what's a clean way of doing it? I had it clean here. This is hard to get clean because it's a slick little argument. Yeah, I'm just going to say we have the same thing. So psi of, I'm going to replace S and D. For all S co-prime to 2N S prime, I have S here minus R minus MN D, which has not changed the fact that this has determinant 1. Everything else is the same, times 1, 2r over s, 0, 1, z, minus psi of 1, 2r over s, 0, 1, z. I mean, this was true for any d. This was true for any d. I'm just replacing the letter d with the letter s. Okay, I want to have both of these in play. S, R, M, N, D of z minus psi of z. Okay. Good. Good. And now I'm going to make a little change of variables in this last one.
Wait, so now S and D are both primes?
S and D are both primes. Now I'm assuming both S and D are prime. I want this formula to hold, and I want this formula to hold. So I better have both S and D be primes co-prime to n.
That's what makes it.
Yep. In this formula, I'm going to make a change of variables. I'm going to try to make this formula look like this formula, and I'll get an extra formula. Okay, in order to get this formula to look like that formula, notice that the inverse, notice that D, let's see, who do I want to work with? Let's work with this guy. D, negative R, negative MN, S, which has determinant 1. The inverse is I flip the diagonal entries, SD, I negate the off-diagonal entries, R, M, N, which is exactly what I see here. So I want to make a change of variables. And the change of variables I want, change, or just replace, it isn't even a change of variables. This is true for all Z. So true for all Z, replace Z by, I want to get rid of this thing and replace it with the D. So I think I want to send Z to okay, I'm going to try. This isn't what what's written here. What's written in my notes is not what I want to do. I think I want to get rid of this. Well, okay, let me try what's in my notes. That's right. That we got that far. We got that far. This is a little tricky, as you can see. I'm going to replace Z by 0, 1 R over S, D minus R minus M N S. That's just the thing that's over there. And then 1, 2 R over D, 0, 1 Z. In this identity. What I don't like is I would think this should be negative 2 RS. In fact, I'm going to go rogue and try. This is going to kill this off. This is going to kill that off. This is pretty close to what I want. This is pretty close to what I want. This is going to end up conjugating that. Okay, let's see what happens. It's going to get ugly. It's going to get worse before it gets better.
I wonder if things got a little strange. I owe something to Mathematica computation.
I think so far everything is exactly as I want it to be. Here, the one thing is my notes are saying an R over S, and I think I want a minus 2 R over S. But maybe there's something that I'm forgetting that's about to happen that will make that. Yeah, I think I want 2 R over S. Okay, let's see. Let's see. So psi of this thing with Z replaced by this. So this whole thing is going in place of Z. This is hitting that. This is hitting that, but I don't like it. So I'm going to change that. So again, I'm going doubly rogue. Hopefully this will work out. Hopefully what I have in mind to have happen is what this is supposed to accomplish. And maybe I got to a slightly different place than the last time I ran it. So that hits that. This hits this and they cancel. And I just get psi of 1, 2R over D, 0, 1, Z. That's this first term. Minus psi of This also hits this. That cancels off. Then I just have dr mns, and then 1, 2r over d 0, 1 z. That's the top line. That's good. That's exactly what I want
It matches what you have.
because it matches what I had above. Right? How about here? Now I have phi. Now this is where I'm going to get a little nervous, but let's see what happens. SR. Ah, this is good. This is exactly what I want. Okay, beautiful, beautiful, beautiful. This thing, then that thing. 1, we're going to reach for Mathematica in a second. Because this is going to get, like I said, it's going to get worse before it gets better. And then this guy, 1, 2r over d 0, 1. Yes, z.
Yep.
Minus,
Matches.
and then that psi of z, psi of 1 minus 2r over s 0, 1 dr mns 1 2r over d 0, 1 z. Okay, not yet, almost. Let me negate both sides. Minus plus, or the exact opposite of what I said is what I wrote. This top line, let's compare this top line with our other formula, which was this top line. Before we switched D's and S's, we had this top line. I hope I got this right. It would be very annoying if I didn't. About to find out. Okay, let me separate these guys before I get really confused. This top line, and now I'm going to make a change of variables. I guess I don't want this 1, 2r over d at the end because I have it everywhere. It serves no purpose. And here I have exactly what I want. Yes. So I'm going to drop I'm going to go rogue a third time and drop that, which I didn't need here. I didn't need it here. And I didn't need it here. And I didn't need it here. Now I'm nervous. Okay, but let's see. Let's just keep going. Let's just keep going. Look at that top line, which is psi of dr minus, not minus, mns z minus psi of z. That's exactly what I have here. The top line matches the top line, which means these two lines also match. Okay. Beautiful. Now I'm happy. Now I'm happy. That means I can leave the top line and replace and get rid of this. No, three wrongs make a right. This is equal to this. Okay, have I convinced you that this top line is equal to this line? And now, once you go rogue with these, you really have to be confident that it's going to work out how you want it to. Yes. Good. I'm happy. And now let me tell you why. I'm going to make a change of variables and get rid of this 2RD.
Now that you group these together.
So this thing isn't here. This thing isn't here, right? These two formulas are equal. I'm going to make a change of variables, make another change of variables. Z gets replaced by 1 minus 2R over D, 0, 1, Z. To get rid of that, the top ones, but I have to put them in on the bottom. So now I get rid of the top ones and I uncross these. But I have to replace it with a minus sign. Okay, we're almost there. I want to express this. I want to express this as this term in front. As this term in front. Yes. I'm going to put it here. Beautiful. Ah, love it. Love it, love it, love it. D minus R minus MNS. I can't just stick it there. I have to put its inverse in. What's its inverse? It's swapping the diagonals and negating the off diagonals. Love it. Okay, check out what we just proved. Let psi1 of Z be defined as psi of D minus R minus MN S of Z minus psi of Z. That's the top. That's the numerator. What's the bottom? The bottom is also psi of this thing times something minus psi at that same something. So this is equal to psi1 of that big something, which I'll call capital M. Where capital M is what's inside of here.
It's equal and then minus 30.
No, it's actually equal.
So you define the sign one.
Yes. Yes. So it's this with the D in front minus this without the D in front, which is exactly psi1 of M, where M is this big matrix. Do you guys see that? Okay, now I need Mathematica. Okay, so who is this big matrix? I have SR, MND, oops, MN comma D, no more M, times 1 minus 2 R over S, 0 over 1, times DR with MNS times, hopefully you're checking that I'm typing this in correctly, 0, 1. Okay, let's expand all that. And we have to remember that the determinant of this is 1. So ds minus MNR is 1. So in other words, whenever I have MNR, I can replace that by ds minus 1. So I'm going to take this whole thing and I will replace any instances of MNR, oops, such that replace MNR by ds minus 1. That's good. It did it for some of them, but it didn't do it for all of them. So let's simplify that. Simplify. Okay, and do it again because you didn't do them all. It didn't recognize all of the MN minus 1s. Let's put some parentheses in case that makes a difference. That's also good, but still not finished. I have, okay, it seems to not notice that then M squared, N squared, R squared, M squared, N squared, R squared should be replaced by this thing squared. Good. Good. I think I'm happy with that. Now expand that all out. Yes. Love it. And give it to me as a matrix looking thing so I can write it down. Okay. Check this out. So M, this is the miracle. M simplifies to 1 negative 2R over D, 2MN over S, 2MN over S, and negative 3 plus 4 over D times S. What is the determinant of this matrix? Yes, This has determinant one, this has determinant one, this has determinant one, this has determinant one. It's very hard to see. Determinant of M is equal to 1. So it's in G, M is in GL, is in SL2R. What's the trace of the matrix? -2 plus 4 over a product of 2 odd primes. That trace is a real number between -2 and 2, strictly. What kind of matrix is M? What kind of motion? We had our classification of motions, depending on the trace. The trace is bigger than 2, we have hyperbolic. The trace is equal to 2 or -2, we have parabolic. The trace is less than 2, then it's elliptic. M is elliptic. We have now psi is an eigenfunction of the Laplacian. Psi 1 is also an eigenfunction of the Laplacian. Psi 1 is eigenfunction of the Laplacian. An elliptic point, an elliptic matrix, elliptic transformation has some fixed point, and then it moves by circles around that fixed point. And this psi 1 is invariant, so there's some sector depending on the eigenvalues. So if the eigenvalues of M are well, they're complex numbers. M is conjugate to some cosine alpha, sine alpha, negative sine alpha, cosine alpha. So M acts as rotation by alpha, or 2 alpha or something, right? Being elliptic means you're conjugate to K, you're in K, you're in some K, some conjugate of K. So if I conjugate this fixed point to I, then it looks like this. The fixed group of I is K, SO2. Whatever I need to move the actual fixed point of M to I.
Well, I mean, in what group does it lie?
In SL2R, if I conjugate in SL2R,
Okay.
then I wind up in K, in the maximal compact, right? This is in K, SO2. So I have rotation by alpha. Maybe this is a rational rotation. What do you think? If alpha is a rational multiple of pi, what do we know about these the trace? Has to be an algebraic integer. Is this an algebraic integer? This is not an algebraic integer, which means that alpha is an irrational multiple of pi. So this element M is an elliptic element that this psi 1 is invariant under, but it has infinite order. I rotate by alpha, I rotate by alpha, I rotate by alpha, I rotate by alpha. I get this dense set of directions, and I'm invariant under all of them. And I'm an eigenfunction of the Laplacian. So there's an argument you can argue by taking a Fourier expansion of psi about the fixed point. Let me, in the interest of time, because there's still a few more things to do, argue by taking a Fourier expansion of psi 1 about the fixed point of M. You can see that the Fourier coefficients have to be equal to themselves times an irrational multiple of pi. You get that the Fourier coefficients are all 0. Fourier coefficients are all 0. Yeah, which means psi 1 is 0, which means psi 1 is identically 0. And what does that mean? Psi 1 was this difference. That means that psi of d negative r negative mn s of z is equal to psi of z only when, for all d and s primes, prime and coprime to n. D and s are both coprime to n. Okay, so we found a whole bunch of functional equations, a whole bunch of automorphisms of psi through this process. Okay, now that we've gotten the rest is going to be easy. Let's pause here for a second.
Like make choices.
We have to conclude. It'll be easy to conclude from here that we get the full automorphy of psi. And once we have the automorphy of psi, phi, the original automorphy I claimed was a phi, which was this Wn inverse of psi, this long Weil element. Okay, so let's just pause here for a second. How did we get here? How did we get here? We started with the functional equation. Okay, how much of this process is invertible? We started with the functional equation. That's what we're given. That's Weil's converse theorem. We're given the functional equation that along a line gave us this identity. And we expanded both of these to get this identity for all chi. The fact that we know it for all chi means we know it for all functions of mean zero, all primitive chi. All primitive chi means we know it for all functions of mean zero. When we know it for all functions of mean zero, we can take this function, which is the difference of r and minus r. This allowed us to play this matrix that we want to know we're invariant under against itself by setting up this difference that's supposed to be zero. We reversed the role of D and S and put an S on top and a D on bottom, and notice that those were inverses as long as R's are negated. And then we made a change of variables in Z. And I mean, I must have made some other choice earlier on in my notes that wasn't the choice that I improvised here. So this was obviously the right thing to do, was to make some change of variables that interlaces the D and the S against one another. And now we got this second identity that we can play against the first. And we observe that this function psi1, which is the matrix that we want to be invariant under, with the difference of psi, this matrix psi1, this identity means that psi of this matrix times z minus psi of z is equal to psi of the same matrix times this big M of z minus psi of big M of z. Okay. That big M turned out to be elliptic of infinite order. And you can't have a function invariant under an infinite order. I mean, that translation by alpha is dense. So you can't have a function that's invariant under that and not be radial in that direction. There's no radial eigenfunctions. How do we know that alpha is not zero?
Oh, no, I was thinking.
How do we know that psi1 is not constant? If psi1 is constant, so we know that psi is a cusp form. By the construction, it's a very good question. By the construction of this function, I mean, it was implicit here. This thing, I'm creating a cusp form. I'm creating what I hope will be a cusp form. I need it to be invariant. So I'm starting with the fact that it's a cusp form. So its limit at infinity is zero. And so the same holds for psi1. Very good question. Very good question. So it's all but the constant Fourier coefficients are zero by this argument. And thanks to Forrest, psi1 goes to zero, or let's just say is cuspidal. Which implies the only constant it can be is the zero, constant zero. Great. So we've shown that we do have anytime we have a prime on the diagonals and multiple of n in the C element, for any r and m that are co-prime, I mean, so that this is a matrix in SL2Z, we have the invariance of psi.
And so where are the choices again in this matrix D minus R minus M?
So for all D and for all S,
we're choosing the other two.
We have the freedom to choose the other two as long as DS minus M and R is equal to 1. I guess, yeah, minus. Okay, So you fix D and you fix S. And then you have the freedom to choose any R. Well, R has to be a divisor of ds minus 1. And ds minus 1 has to be, so D and S have to be, D has to be S inverse mod N. Okay, so once you choose any D and any S, which is D, which is a prime, that is, and both of these are prime. Yeah, I said that, both of them are prime. They're multiplicative inverses mod N. So ds minus 1 is a multiple of N. When I divide by N, I get some number. Take any factors of that number.
You can find these times.
Ah,
These like times and corrections.
that is the next thing that's exactly what we're going to input. Okay, so now I want for any A, B, C, D with A, B, C, N, D in gamma naught N, I want that I have this formula psi of A, B, C, N, D, Z is equal to psi of Z. Right? That's the last thing I have to prove. I don't know that to be true yet.
This would be the full.
That's the full, that would finish the theorem, right? That would imply that psi is on gamma naught D, and which means that phi, which is psi of Wn inverse, is also on gamma naught N, which was the thing that I claimed it for phi. We've been working with psi all along. Same thing.
You have translation already.
Bingo. By the Fourier expansion, by the fact that we wrote down psi as a Fourier series, by Fourier series of psi, we have that psi of 1, 1, 0, 1 of Z is automatically invariant. So, what can I do? I want to write my A, B, C, D, C, N, D as something that I know I'm invariant under, multiples of this, times things that I also know I'm invariant under, which is D minus R minus Mn S. But I also have another bit that I'm invariant under, which is this. I'm invariant under this, then I'm invariant, or rather, if I put psi here, psi is invariant under this, psi is also invariant under this, psi is also invariant under this. Can I find such a representation? So can I find such a representation of this matrix in terms of ease? Well, let's see. Let's multiply this out. This product, right-hand side is equal to, okay, 1 times D, I get a D minus MNU, right? And then I get a negative R plus US, and here I get a 0 and a minus MN and S. And now I multiply by 1V01. 1V01. I could have, yes. It's embarrassing how difficult it is for me to do these calculations. Okay, so that's a D and then that. And then the bottom row is also minus MN. Good. And this row is something really nasty. D minus MNU times V plus minus R plus US, whatever it is, I don't actually care. And down here I have a V minus MVN plus S. And I want this to match up with ABCND. Okay, well, one thing is easy. I set M to be minus C. Okay, so now I look at, can I find this? D minus M is plus C, and U is equal to A. i.e., I've already set, does there exist a U? I'm free to choose any U here I like. Does there exist a U such that D which is equal to A minus CNU is prime.
We have relatively prime.
U is my parameter, so this is the arithmetic regression. This is an arithmetic regression of step NC, of modulus NC with shift A. What do I know about A and NC? Well, they make an SL2Z matrix. And A and NC are co-prime. Good thing we know Dirichlet's theorem.
It's kind of funny, right? How you apply a sledgehammer and you get one.
Yep. By Dirichlet's theorem, prime and progression, there exists a D such that there exists a U, there's some number U such that D defined to be A minus C and U is prime. That's cheating. That's cheating. We're about to cheat again. Look down here. I need little d to match with MV. Negative M is C. C and V. If you gotta cheat, you gotta cheat. Plus S. And I want S to be prime. I.e. I want S to be equal to D minus Cn V. And of course, D and Cn are also co-prime. D and Cn are also co-prime, which implies, and I want that, and I need S to be congruent to D bar mod N. And these two arithmetic co-prime arithmetic regressions give you some arithmetic regression in which you're looking for S, implies there exists an S prime, again, this is Dirichlet. And now we're done. So we found a D. We
reconcile these two arithmetic regressions.
Yep.
With, I don't know, product or whatever.
Yep.
Things on it.
Yep. So let's summarize. We're almost out of time, and that's we're really going to get it. Find U such that D is equal to A minus C and U is prime. The point is here we want to find V, and U and V are completely free. They're independent of one another. Find V such that S is congruent to D. Okay, S is defined by D minus C and V is prime, and S is congruent to D bar mod capital N. Then psi of A, B, C, and D of Z, which is also equal to psi of this whole thing, 1 U 0 1, with this choice of U and this choice of V, we found this prime D, we found this other prime S, they're co-prime to one another. They're inverses mod N of one another. This is Cn, and this is, I don't even care what this is. This is just something. 1 V 0 1 Z. Okay, but psi is invariant under translation. Psi is invariant under all things of this form with D and S prime. And psi is invariant under translation. And that, ladies and gentlemen, is the proof of Bayes' Converse theorem.
And so really what you needed wasn't primitive characters, it was primitive and prime.
That's right. I only needed D's prime, but I don't know which primes I would
So you
need.
just choose all of them. Like, and now-
Sure. Yeah,
No.
all the primes co-prime to N would be enough. Yeah, I didn't need all the twists. That's what I mean by you can start taking this proofs like this and find even more clever ways to get the functional equations that you need out of the L function. But you see what we did? We took the twisted L function functional equations, converted them into automorphy. That's the converse statement. We prove that this psi really is an automorphic, not yet representation, just an automorphic form.